So we had spent some time working with the resonant frequency, half-power frequencies, and whatnot on this particular circuit, and we wanted to we talked about what the admittance was of a circuit that was at or near resonance, and we wanted to go through this. Given this current as 500 milliamps times the cosine of omega t, we wanted to come up with what this output voltage is here, V naught. So we'll go through that process. What we had finished up last time, if you look back to your notes from last time, is that, and I'll write the equation over here, that the admittance for this thing, we had taken a circuit very similar to this that had a resistor, it had a capacitor, and it had an inductor. And we said that the admittance for this thing was equal to 1 over R times the quantity 1 plus J times omega plus omega naught times omega minus omega naught divided by omega times the bandwidth. Okay, and then we talked about an approximation of that, and I'll go into that in a little bit. But that's the equation that we derived. So I'd like to go ahead and use this thing for this particular problem and come up with the admittance here. So we could say then that Y is going to be equal to, the admittance is 1 over, what was our resistance, 2,000. And remember last time we had a little bit of confusion, or I had a little bit of confusion on the capacitance. I started out with it being equal to half a microfarad. Then my numbers didn't line up, so I changed it to a quarter microfarad, and I have corrected that here, a quarter microfarad. So I have 1 over 2,000, because that's the resistance, times then 1 plus j, of course j is square root of minus 1, so we're back into complex numbers here, and then omega plus omega naught. Okay, remember we're going to drive this at 10,500, that's our omega, and our omega naught is the resonant frequency at 10,000, so I am going to have omega plus omega naught, that should be 20,500, and omega minus omega naught should be just 500. So I'll have then 20,500 times 500 divided by the bandwidth. What do we have for the bandwidth? 2,000. And omega was 10,500. Okay, so that's our calculation. So we just have a constant times a complex number. And when you go through that, this turns out to be equal to 0.5564 at an angle of 26.02, and that would be Siemens, inverse of ohms. Okay. So that should help us get the voltage, because we know, of course, by Ohm's law that voltage is equal to current times impedance Z, so that would be also likewise equal to the current I divided by the admittance Y. So if I put this in here, we have 50 times 10 to the minus 3 at an angle of 0. Okay, that's that guy there. Divided by the admittance, so 0.5564 times 10 to the minus 3 at an angle of 26.02 gives me my voltage. So let's see. So we come up with 89.87 at an angle of minus 26.02. That should be volts. Okay. So that would be our answer. And that's at this frequency. That's this is exact. At omega is equal to 10,500 radians per second. Questions with that?
What was the unit used
Admittance? Yes. This, that's 1 over ohms, which is Siemens. Other questions? Okay. Well, when we had to derive this equation, we also looked at an approximation. So I'd like to go back and look at that one now. So we can say then with the approximation, so the equation for the approximation, we saw that if our frequency, if the frequency that we're going to be driving it at is between omega 1, the low power frequency, and omega 2, which it is, our frequency, remember, is 10,500, we could use this approximation that the admittance was approximately equal to, I guess I'll use that symbol, approximately equal to 1 over r times 1 plus j, and then we just had omega minus omega naught divided by the bandwidth over 2. So if I did this, I get 1 over 2,000 times 1 plus j, and omega minus omega naught is going to be, what, 500? Divided by the bandwidth over 2, 2,000 divided by 2, using those quantities that we still had from the previous problem. So when you run through this, the admittance turns out to be equal to, I don't think I solved it completely, 1.1180 at an angle of 26.57. So the angle is fairly close. And I still had to divide this by 2,000. I still have that resistance in there. Of course, that's Siemens. I'll leave that. I don't know that I need to finish that up because I'm just going to use it to get the current. We could say again that V naught would be equal to the current times the impedance. Actually, I'm not using that to get the current. I'm using that to get the voltage, which would be the current divided by the admittance. So we'll take the current value as what it was before, 50 times 10 to the minus 3, because it was milliamps at 0. And then I'm dividing this thing by 1.1180 over 2,000, an angle of 26.57. So this turns out to be 89.44 at an angle of minus 26.57. That would be volts. And this is approximate. How did we do? If I go, we look at what we got there. Oops, there we are. So 89.87 versus 89.44, that's pretty good. The angle's off a little bit. If I just look at the difference in the magnitudes, so percent error or percent difference in the magnitudes, we're going to have that's 89.44 minus 89.87 divided by 89.87 times 100, which gives me about, I guess I'll take the absolute value of that. There we go. 0.48%. So less than 0.5%. So it's not too bad. Like I said, when we saw this equation here, with all our computational tools nowadays, I don't know that that's a big deal. Dealing with this equation here is really probably pretty easy if you have a calculator. But if you were to do it by hand, then this equation is certainly more attractive. Sometimes see those approximations left over when we used to have to do more stuff by hand. Questions with that? Yes?
Why was your
why? Admittance?
Why is that not in the discount?
Because I left the 2,000 in it. Yeah. So I could have, if I wanted to, said that this was 1.1180 divided by 2 at 26.57, and then that would have been millisiemens, which is fairly close to what I had last time. What was I trying to pawn off last time? 0.564 milli, yeah, so we're pretty close to that. Other questions? Okay. Well, let's go on and look at a couple more problems before we wrap up this section. Remember with this, when we started this problem, we started parallel resonance when we derived this equation here. I'm going to go back and look at series resonance. So now I put my elements in series and go through a very similar process. Instead of talking about admittance, I'm going to talk about impedance. So I could say that the impedance Z was equal to R plus J omega L minus 1 over omega C. Is that right? And we could go through a very similar process. Maybe I'll zip through this a little faster than we did last time. We'd have R times 1 plus J omega L over R minus 1 over R times omega, what do I have, omega C. Then I can multiply everything by, what would work here? Omega naught over omega naught. Yeah, why don't I do that? So I could say multiply by omega naught over omega naught, which is going to give me R times 1 plus J. And I'm going to have omega naught times L over R times omega over omega naught. So yeah, if I omega naught over omega naught minus then 1 over omega naught RC times omega naught over omega. Again, both of these, if you were to cancel out the omega naught, you'd get back to what we had in the line before. The reason for doing this is we recognize omega naught L over R, or 1 over omega naught RC. Anyone made their 3x5 card with series on one side and parallel on the other? Probably going to do that before the final, right? Okay. Well, as you go through that process, you'll recognize those as Q, right? So if that's Q and that's Q, we could factor a Q out of this thing and say that the impedance is equal to R times 1 plus JQ. And then we would have omega over omega naught minus omega naught over omega. It looks very similar to what we had last time. We got a common denominator. Then we had the difference of squares. Yes?
The omega in the top three equations is the same as omega.
I don't think so.
How did you switch to omega naught in the third equation?
Right here? I took this equation and I multiplied this equation by 1, which looked at was omega naught over omega naught. So if I took this one and I multiplied by a weird looking 1, I got the third equation. Other questions? Okay, so if I go through this, getting common denominators and dealing with the difference of squares, we would get our final answer here equal to R times 1 plus J omega minus omega naught times omega plus omega naught divided by omega times the bandwidth beta. Okay, and that's exact. And just like for the admittance, it's also true for the impedance. We can have an approximation. We can say that if our omega is that we're driving this at is between our half-power frequencies, omega 1 and omega 2. And those of you that did the lab yesterday, omega 1 and omega 2 make more sense now, hopefully. Yeah, so good. Those of you that are in the lab tomorrow, bear with us, and hopefully you have a bit better understanding of that after tomorrow. Anyway, if we're driving between those two frequencies, we can say that the approximation, and again, with all the calculators and computers nowadays, I don't know that this is a big deal, but the approximation for the impedance, we could say that Z was approximately equal to R times 1 plus J. We'll have omega minus omega naught divided by the bandwidth over 2. Double check those here. Yeah, should be good with that. Okay, and obviously your approximation is better the closer you are to the resonant frequency.
Mark, is it only for a series circuit?
Yes, it would only be for a series circuit. If we went with a parallel circuit, then we're going to, of course, go back to this. What if we have a combination of a parallel and a series? Then we're going to have to start the derivation all over again.
We're going to define that for a parallel circuit.
We define it with admittance.
Oh, right.
Yeah.
So the difference is only 1 over R.
Yeah.
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 So the changing the would our admittance then be the same in series?
Well, if you think about it this way, I mean, you say, and you make a good point, that the only difference is 1 over R. At resonance frequency, the only thing is R, right? And if we compare admittance to impedance with no complex portion, all we have is R. So indeed, the only difference is 1 over R. Now, if someone comes along and maybe puts another capacitor or something in here, then it's a whole new ball game, because we're going to have to redefine this impedance here. Another derivation. Yeah, these are specific cases, but they come up quite a bit. Well, so we've opened the can of worms on series resonance. Let's give this a little more thought with a problem. So let's say that I've got a problem like this. So we're not given very much about the circuit. We just know it's series resonance. We're told what the resonant frequency is, omega naught, 5 mega radians per second, or 5 million radians per second. Omega 1, 4.5 mega radians per second. Capacitance, 0.01 microfarads. So I guess we know C, but we don't know R and L. And in fact, what we are trying to find is the quality Q, the resistance R, and the bandwidth beta. Okay, so let's see if we can do that. If you had your index card, you'd flip that to the series side, right? And you'd recognize that whether it's in series or parallel, but the resonant frequency omega naught is equal to 1 over the square root of CL, right? Yeah. So if I rearrange this, I could say that 1 over omega naught squared is equal to CL, or that L is equal to 1 over omega naught squared times C. So I could say that this was 1 divided by 5 times 10 to the 6, because we've got omega, we've got that squared, and then I've got to multiply it by C, which was 0.01 micro, 0.01 times 10 to the minus 6. Which we end up with 4 times 10 to the minus 6 henries.
For the omega naught, that's 10 or 5 microradians?
No, mega.
Oh, mega. It's to the positive 6.
Yes. Of course, then we go down to lab, and the capacitors are labeled with the capital M, which means micro. But that one's fairly easy to distinguish, right? Because how many megafarad capacitors do we think we got laying around in lab? Probably less than that. I suspect if we look real hard, we could find a 1 or 2 farad capacitor.
How big would that be?
Well, it depends on how much voltage you want it to be able to endure. I think if you go online, or maybe some of you are the kind that set up audio systems to bust out the back windows of cars, they use pretty big capacitors for that. It's fairly low voltage, maybe 20 or 30 volts, and I think a farad capacitor is about the size of a thermos. Yeah. So that's why I was being a bit facetious, saying I don't think we have any megafarad capacitors laying around the lab. We good to continue on? So we've got L. That's good. I guess we didn't want L, did we? That was kind of a fun tangent, but well, let's see. We'll just say L. There we go. We got L. Maybe that'll be useful for something, hopefully. Well, let's see. Could I get omega 1? We got omega. Well, I got omega 1. I want the quality. Well, could I try this? I know that omega 1 is equal to omega naught times 1 over 2q, and I have to take the negative when I want omega 1, plus the square root of 1 over 2q squared plus 1. That was an equation we had, and that worked for both parallel and series, didn't it? So I could say then, if I were to divide both sides by omega naught, omega 1 would be 4.5, omega naught would be 5, and you might say, well, that's 10 to the minus 6. Well, it's 1 over the other, so it cancels out, right? That would then be equal to minus 1 over 2q plus the square root of 1 over 2q squared plus 1. Okay. So we could get q from that, right? Well, yes and no. Now you could do it with algebra. I think I got the notes here for algebra. It's about 3 or 4 pages of algebra. You start by squaring both sides, and away you go. Lots of fun. Okay. You could throw it into your calculator. You could use an algebra tool, Maple, MATLAB, something like that. Yes? Yeah, there's actually another way. We'll talk about that. Yeah. So, yeah. So I mean, we could solve this and get Q if you use a solver, some sort of numeric method or something. You're going to come up with Q as about 4.74, which is fine. I mean, that's a lot of algebra or using some other technology. But some people, I think they're recognizing there might be another way. And I don't want to put words in your mouth, but one other way would be to look, say that omega naught, the resonant frequency, and we talked about this last time, the resonant frequency was not the average of omega 1 and omega 2, but was, I should say, is not the arithmetic average, not the average that we normally think of, but was the geometric average, wasn't it? That's where we had the square root of omega 1 and omega 2, didn't we? So we could say then with this, maybe I should put an or here, we could say that omega naught squared divided by omega 1 is equal to omega 2. So omega 2 turns out to be equal to, well, let's see, omega naught 5 times 10 to the minus or plus 6 divided by omega 1, which is 4.5 times 10 to the 6, and the numerator needs to be squared. And this turns out then to be equal to 5.56 mega radians per second, which seems about right. And then my game plan on that, and I don't know if this is what others were thinking about. You may have yet a different way. And there's lots of ways to the answers here. Unfortunately, there's a few wrong ways too. But if I say omega 2 minus omega 1 That's the bandwidth, isn't it? And that's good for both series and parallel. So if I take omega 2, we have omega 2. Where's omega 1? That was given. So that turns out to be about 1.056 megaradians per second. Well, what good is that? Well, we know that omega naught over the bandwidth is equal to Q, isn't it? So I've got omega naught. I now have the bandwidth. So this would be 5 times 10 to the 6 divided by the bandwidth, 1.056 times 10 to the 6. And the quality is unitless, turns out to be 4.74. So you can use, you could use a really fun trip through algebra here if you wanted to, or you could use some brute force solving methods. Or sometimes if you're really good, you can come up with the equations and avoid all of that. Questions thus far? So we got Q. The nice byproduct of that is I got the bandwidth beta. I've got L. So I need R, don't I? How could I get R? Now let's see. We could say that we're looking for R. We know that bandwidth for series, and this equation is unique to series, that bandwidth is equal to R over L. So I could say that R was equal to the bandwidth times L. So I guess I'm glad I got L, right? So the bandwidth, we found that is 1.056 times 10 to the 6th times L, which we found was, yeah, right there, 4 times 10 to the minus 6. So we get about 4.22 ohms. Another way of doing that would be to recognize that Q quality, and this is unique to series also. Parallel is going to be a little different equation. It's going to be equal to 1 over R times the square root of L over C. So we could rearrange that and say that R is equal to 1 over Q times the square root of L over C, and we would get exactly the same R. Questions with that? Pretty low R, isn't it? And those of you that were in lab yesterday may be scoffing at coming up with an R, although our filter was very different. I mean, we were running at, what, 10K? We're talking about running here about 5 million radians per second. So divide that by 2 pi and you'll come up with whatever the hertz are. But this is a much higher frequency deal. But anyway, coming up here and putting 4.22 ohms, back to what I was saying, some of you that were in lab yesterday kind of scoff at that, right? What'd you come up with for the resistance in your inductor? It was probably 60. If we had a bigger inductor, it could be a lot larger. I mean, we had inductors on that same board that were, what, 600 ohms? And what about the function generator? What resistance did we have there? Another 50? Okay, so that begins to kind of spoil the fun at 4.22, doesn't it? Yeah. So that's why a lot of times students next term, we'll see this again, they'll have this really great bandpass filter designed. They get down to lab, they set it up, turns into a low-pass filter. It's because they have way too much resistance. So that'll give us something to worry about and work on next term. So we're pretty well set with this section, talking about some basic series and parallel resonance. It came up earlier in the lecture today, and I'm glad it did, because I was going to talk about it, and I'll mention it although a little bit quicker. We looked at the cases where we had a series arrangement of a resistor and a capacitor, and then an inductor, like that. And whether you want a band pass filter or a band reject filter depends on where you're tapping the filter, so to speak. I mean, if we take the voltage across here, as this goes to resonance, this part goes to 0, right? And that's going to give me a band pass, isn't it? If, however, I look at the voltage across here, some of you will recognize this from yesterday in laboratory, that goes to 0 and we get what? That's our classic notch or band reject, isn't it? So depending on where we take the output on this, we can get a different filter type. So that's simple series. If I look at parallel, we have a resistor, capacitor, and inductor. Okay. Usually you just end up tapping across there, and depending on the values, you could have different ones. But the point that I wanted to make here is we've got nice equations for this one now. We have nice equations for this one. But if someone comes along here, like I mentioned before, and maybe they put a capacitor in here, it's a whole new thing, isn't it? We would have to come down here and draw this model. What would we have? We'd have a resistor, we'd have a capacitor, another capacitor, and we'd have to look in here and we'd have to talk about what the impedance is and start from scratch, wouldn't we? What if someone came in here and maybe they put a capacitor in here? Now, what would you have to do? You'd have to come down here. Let's see, is this going to be the same one? Mirror image, kind of. Mirror image and upside down. And we'd have to look at what the admittance here is and start all over again, wouldn't we? So the equations that we have are for very specific circuits. There are circuits that come up quite a bit, but there are certain limitations to them. So be real careful of that. I think you've got a homework problem where it asks you to go into a new realm here. Questions of that? Well, where do we go from here? We have one area to finish up. So the rest of our time in here, we got about 3 lectures. We'll be left talking about Fourier analysis. So how do we model a periodic but maybe non-sinusoidal? I mean, you could model a sinusoidal wave with a Fourier series, but it would be kind of silly to do. And there's all kinds of waves that are periodic but non-sinusoidal. We might have a fully rectified wave, or maybe you're really cheap and you're just going to do a half rectified wave. Okay, or maybe you're going to have some sort of a square wave, like this. Or maybe we'll look at, I think last term, didn't I bring in a light dimmer? We talked about, we took this sinusoidal wave, and we said the dimmer really just turned it on during this region and turned it on during this region, on during this region and this region, so we really ended up getting a wave that looked like this. Okay, and when you change the dimmer knob, you can get these closer together, right, or further apart. Sometimes they talk about duty cycle on something like that. Well, all of these waves that I've drawn up here are examples of periodic waves. They're all waves that we use in real life, and we'd like to be able to talk about those mathematically, and what we're going to use is Fourier series. Okay. Fourier was developed by Jean-Baptiste Joseph Fourier. Was actually done for his work in heat transfer. So this is something that you can apply really to anything. You can imagine it with heat transfer as temperatures, they go through cycles. That might be something you want to do. We usually see this in electrical because it fits pretty well in electrical. Are there certain stocks out there that might have kind of a periodic model? Well, definitely. So I mean, you could apply this to a lot of different things, but it fits pretty well in electrical. So we're going to talk for a couple days on how to do this. That'll actually position us at the beginning of next term for the electricals really well, because we'll pick up on that point and go into it in quite a bit more detail looking at this. So that'll be the last official area that we cover in this class, and then we'll spend at least a couple days going through some review questions, recapping the entire term, going through some review, talking about maximum power transfer, some of the things from the beginning of the term as we get ready for the final. So that's where we will go. Take care till then.